Hello everyone. Today we are going to discuss combined cycle power plants. So what we are doing in combined cycle power plants, that we are using both the Brayton cycle as well as Rankine cycle. So this is typical Brayton cycle and this is Rankine cycle. So what we are exactly doing, we are using the energy of the exhaust gases. In a heat exchanger, this is a heat exchanger where the steam or water is taking out the heat from this exhaust gases, and after taking the heat the expansion is being done in the steam turbine. So generally the gas turbines operate in a temperature range of 1400 to 1500 degrees centigrade, and the exhaust of these gas turbines are typically in the range of 700 to 800 degrees centigrade. Now when the higher temperature exhaust of gas turbines left to the atmosphere, so this is just a heat or available energy loss. Now if we use this available energy to heat this steam as visible from 2 to 3, this is a typical example of heat recovery. Therefore, as visible from the TS diagram, this is the gas turbine Brayton cycle, which is topped over the Rankine cycle. Therefore, the combined cycle efficiency is given by W gas turbine plus W of steam minus W compression divided by heat input. This is the calculation of efficiency. Now why do we have done this minus WC? Because the gas turbine network W net of gas turbine is given by W turbine minus W of compression. Therefore this is here taken as minus. So this is the basic of some combined cycle power plants. So combined cycle power plants are one of the most important topics, as continuously numericals are being asked in civil services examination, engineering services examination, forest services, various university examinations. So this was the basic of combined cycle power plants. Now generally one objective can be asked to arrange the efficiency increasing or decreasing order. So generally gas turbines efficiency typically lies in the range of 25 to 30%, whereas the steam cycles or Rankine cycle efficiency lies in the range of 37 to 40%, whereas the combined cycle efficiency, since we are using the waste heat of the exhaust gases, it comes around 45 to 55% typically. Therefore this is one of the improvement over the typical cycles. Now I have taken one problem, basic problem, and similar problems are being asked continuously in mains examination of engineering services and civil services examination. So let us try to solve this problem. So this is the basic combined cycle problem, of combination of gas turbine and Rankine cycle for steam turbine. So in this given data, we have the pressure ratio, that is Rp is equals to 8. Entry of the air to the compressor, that is T1, is at 300 Kelvin, and at the inlet to the turbine, T3 dash has been given as 1300 Kelvin. Isentropic efficiency of compressor has been given as 0.80. Efficiency of turbine is 85%. It means that compressor and expansion is not isentropic. Therefore, so let us suppose that this is 2s point and this is the 4s point. Further, the data, the gas turbine exhausts are leaving the heat exchanger, that is T5 dash at the rate 450 Kelvin. Now coming to the steam cycle or Rankine cycle. So 1 to 2 is the pump work, then 2 to 3 is the constant pressure heat addition in the heat exchanger, where heat is exchanged between the exhaust from the gas turbine and the water, which is being converted to the steam at 7 megapascal and 400 degrees centigrade. Therefore, H3 can be determined from the steam table. H4 can also be determined from the steam table or Mollier chart by equating the entropy. Since H3 and H4 is an isentropic process, therefore efficiency will remain the same. Therefore, from the steam table, H3 31411.4 kilojoule per kg, H4 is 2073.04 kilojoule per kg, and S2 is equals to H1. I am assuming, since we are neglecting here the pump work, it is around 144.73 kilojoule per kg. So this is all about the given data. Now let us try to solve this problem. So first, coming to the analysis of gas turbine. Therefore, since pressure ratio has been given, therefore applying T2s upon T1 is equals to Rp gamma minus 1 upon gamma, that is 80.4 divided by 1.4, taking gamma as 1.4. T1 is 300 Kelvin, therefore T2s comes out 543.43 Kelvin. Now 1 to 2 is not the isentropic process, therefore now we have to determine the T2 dash. Therefore compressor efficiency has been given, therefore eta compressor has been given as 0.80. Therefore T2s minus T1 divided by T2 dash minus T1. We have the value of T2s from the first equation. Putting this, T1 was given as 300, T2 dash we have to determine minus 300. Solving this above equation, we determine the T2 dash as 604.29 Kelvin. Now T3, that is inlet to the T3 dash, that is inlet to the gas turbine, has been given as 1300 Kelvin. Now taking the Cp as 1.005, we can determine the heat input in combustion chamber. That is Q in is given by Cp into 1.005. We are considering the per kg of Q heat supplied per kg of gases. So T3 dash is 1300 minus 604.29. So heat input in the combustion chamber can be calculated from the above equation. Now we have to determine the work done in gas turbine. That is W net in gas turbine. Therefore, it will be around Cp T4 dash minus T3 dash minus Cp T2 dash minus T1. Now we don't have the value of T4 dash. Similarly, this can be obtained as we have done in the procedure for the compressor. That is T3 dash by T4s is equals to 8, that is pressure ratio 0.4 1.4, that is gamma minus 1 upon gamma. From this, T4s can be obtained as 717.658 Kelvin. Now this is not an isentropic process, therefore eta turbine has been given as 0.85 and it can be written as from the above, that is from here we can determine eta turbine is equals to T3 dash minus T4 dash divided by T3 dash minus T4s. From this equation we can obtain the value of this is T4 dash and this is T4s. From this T4 dash can be obtained as 805.014 Kelvin. Now we have the value of T40. From this, W net can be calculated. This is coming around 1.005 into T4 dash is T805.04 minus T3 dash, it should be written reverse, that is 1300 minus 805.04 minus 1.005 into T2 dash minus T1, that is 604.29 minus 300. So calculating this, it is coming around 191.623 kilojoule per kg of gases. So this is the W net, that is we are obtaining from the gas turbine. Now let us analyze steam cycle. So in this steam cycle, first we have to determine the proportion of gases in the gas turbine vis-a-vis the proportion of steam in the Rankine cycle. Therefore, from the heat exchanger equation, we can write that heat given by, if mass of gas is the gas of exhaust gases in the gas turbine, then heat output, that is T4 dash minus T5 dash, is equals to mass of steam, that is heat absorbed by the water in the Rankine cycle, that is Ms S3 minus S2. Here we have to multiply Cp. So we have the value of S3 and S2. T4, T5 dash we have. T5 dash is 450 Kelvin, which was given in the problem. Therefore, from this it can be obtained as mass of steam versus mass of gas is equals to 0.12. That is, for 1 kg of gases, 0.13 kg of steam is required. Now, coming to the efficiency turbine W turbine work done. Therefore, W turbine work done is given for 1 kg of gas here. We have mass of steam 0.13 kg, and it is coming around S3 minus H4. Therefore, this is the mass of steam into S3 minus H4. Therefore, 0.13. S3 value we have obtained from the steam table, 3411.48 minus 2073.048. This can be calculated as 173.89 kilojoule per kg of exhaust gases. Now we have to eta combined cycle we have to determine, which can be determined as W gas plus W steam turbine divided by W net heat input. Therefore, we have determined the W gas as 191.623 plus 173.89 divided by 1.005 into W input, that is Cp into T3 dash minus T2 dash. So eta combined, this is 191.623 plus 173.89 divided by 1.005 into T3 dash is 1300 minus T2 dash is 604.29. Solving this, so eta combined is coming 52.27%. So in this way we have solved the problems of combined cycle, and these problems are being asked in 20 marks, 25 marks in engineering services, civil services and forest services examination. So to give you conceptual clarity also, I have solved this complete numerical, and these problems are also very common in university examination. So thank you for watching the lecture. We will meet again in the next series of power plant.